Welcome everybody at the 8th session in the series about digital innovation powered by Bouwen and Staal. Today we have Zwart Jansma visiting us, and in a special Anurag Bhattacharya is joining us. Hi, welcome.
Hi guys.
Can you do a little introduction about yourself? Who is Anurag?
Yeah, sure. First of all, greetings, and hope with all my heart that you and your loved ones are doing well in these times. It's such a great pleasure to be here, and thanks for inviting and giving me this opportunity to talk with the Bouwen and Staal and this interesting series with deals with innovation. My name is Anurag Bhattacharya. I'm an architect and design coordinator with Zwart Jansma Architects. I've spent more than 7 years in the architecture and construction industry, and my main focus had been in designing high quality built environment, and also kind of pushing the boundary of innovation in terms of construction technology. So I'm really excited to be here, and let's see what comes out of this.
Yeah, definitely. Nice to have you here today, Anurag. The reason why we are doing this webinar series is kind of to benchmark the current state of art in computational design in the Netherlands. And what we actually want to achieve is to inspire each other and motivate each other in order to start learning these kind of new technologies, so that we as an industry can further grow. So that is actually our main goal of doing this webinar series. So it's great to have you here today. If we look back in time to all the presenters we had so far, we mainly had structural engineers, we had some platform services, and you are now the second architect, so who is presenting her. So that's really a nice mixture of different presenters. So before we start, we have to go over the house rules. So if everybody can turn off their microphone and turn off their camera, then the broadcast will be as pleasant as able. And questions you can ask them in the chat box, but we will answer them at the end of the presentation. So hopefully we can get some interesting discussions going around. And if you want, you can post them in the chat box, but you can also raise your hand, and afterwards you can just ask your question live with your microphone and video shared if you desire that. So Anurag, the floor is yours. I'm really excited.
Oh, thank you very much. And so let's begin with it. So I think I'll start by sharing my screen first. So today I'm going to focus on the value of parametric design workflow and the cross-disciplinary collaborations within our projects at Zwart Jansma, and what does that mean in terms of designing as an architect for us. So coming to the topic of today's webinar, it's architecture shapes performance. Generally, when you start designing, there are certain factors you take into account. For instance, the context, the function, the climate performance, structure, architecture vocabulary, etc., etc. You start thinking how you can enhance the performance, and it does inform architecture in a manner. But it can also be that the architecture, the form, the materials, and the structure concept used, that can enhance the performance as well in terms of climate, building physics aspects. It's a sort of a loop, how I see it, and today we'll be looking at Shaded Dome and its application in the Freedom Museum to understand this better. But very quickly, for those of you who don't know us, we are ZJA. We are an internationally recognized architectural practice founded in 1990 by Moshe Zwarts and Ryan Jansma. And we are located in the city of Amsterdam. As a practice, we operate at an intersection of architecture, design, and technology. Our projects range from large-size, complex infrastructure projects, be it the stations, bridges, theaters, stadiums, and mainly we are active in Netherlands, Belgium. Now we are also getting into South Korea and Scandinavia. The office is led by Ryan Jansma, Rob Torsing, which you see on the top left corner of your screen, Randall Top, and Ralph Keft, along with a creative team of international professionals coming from very diverse nationalities. We draw upon state-of-the-art technical expertise thanks to our in-house R&D groups, where we focus on computation design, various methods of how you can also introduce structural optimization in the design workflow. And we are also now really focusing on the SDGs, which are the Sustainable Development Goals, which have been lined by United Nations, and to see how our design can also be informed with these SDGs. And also we are now trying a bit in the realm of mixed reality to see how that can also influence the design workflow, and this virtual environment, how can we create this. We are more than a typical architectural firm. We are not just architects, but we are actually all of these things that you see on your screen. And all these expertises find their ways in our projects via exhaustive research and design. ZJA has been a big advocate of cross-disciplinary collaborations to achieve outstanding levels of innovation. We believe in architecture that is technologically advanced, sustainable, and beautiful. These all contribute to the building's character, but in my opinion, it's more than that. Buildings such as the Freedom Museum in Groesbeek that you see on your screen performs in terms of the performative aspect, such as lowering the overall building's energy load while ensuring more environmentally sensitive design. I will talk about the project in more detail in a moment, but first let me give you a bit of a context, what exactly it is. What you see on your screen is the old museum complex, and it was opened in the year 1987. And this building has been using the remains of former Nielche and has been exhibiting documentation of Second World War. In the course of time, with many buildings as it goes, there's an increased need for extra surface area, and the museum also wanted to be able to offer a new program that would be more in line with modern requirements. So there had to be a larger building, but one that would fit within the budget. It was also our wish to preserve this echo of the Anton Cronin's characteristic dome, as you see on your screen. This referred in its shape to the parachutes of the thousands of American paratroopers who were dropped during the Operation Market Garden and Great Rhineland Offensive during the World War. A solution that met all requirements came in the form of shaded dome technologies. But, well, what is a shaded dome? Everyone would ask. It originated from the idea of developing climate-controlled indoor sport facilities in hot-dominated physical environments. The exploration began keeping in mind the FIFA World Cup 2022 in Qatar, which also needed these kind of adaptable indoor training facilities. How could we protect the athletes from the heat? The next question came. The solution to the challenge came in the form of shaded dome. It comprises of air-supported pneumatic structure, which you might have seen in your nearby tennis or football facilities. These inflatable structures offer a perfect solution when it's impossible to perform activities in the open air all year around. And then we introduce a tensile membrane structure or a tent on top of it. The combination of the dome and the shade forms a hybrid structure, and which we call the shaded dome. 3 Dutch companies, ZJA, Royal HaskoningDHV and Poly-Ned, teamed up and took up the challenge to develop an eco-friendly, semi-permanent and innovative idea. One of the key drivers was being able to quickly assemble and disassemble a shaded dome within a matter of just 2 to 3 weeks. Talking about the composition, as I've already mentioned earlier, it comprises of an air-supported dome. This is the core of the shaded dome and operates in principle similar to a generic air dome, allowing air pressure to act as the main load-bearing system. The air-supported dome is then covered by a custom-made steel cable network. This cable network dictates the overall shape of the dome and carries the majority of the loads. This is followed by a grid of spacers, or struts you may call, which are these verticals at cable net intersections that form a link between the air dome and the membrane layer or the shade on top. These spacers maintain the cavity spacing and transfer the overpressure from the air dome to the shade, while external loads such as wind forces are transferred in the opposite direction from the shade towards the dome. The shade also, on the other hand, shields the dome from excessive solar radiation, wind and precipitation loads. Just coming back to some basic fundamental principles. Whenever you talk about a tensile fabric structure, they're generally tensioned and they achieve their structural stability due to their doubly curved surface or anticlastic shapes. Here it is no different in shaded dome. The global convex curvature, which you see, is the result of the overpressure within the air-supported dome, which are represented by these blue pluses, and the force being transferred to the above shade via spacers being represented by these blue arrows on your left-hand side corner. These patches contribute to the local concave curvature. The combination of a global and a local curvature within tensile membrane provides stability to the form. At the periphery of the shaded dome, in the two corners you see here, the membrane is fixed to the foundation by either anchors or suspension cables. Let's talk about the climatic aspect of it. The air cavity between the shade, which you see here, and the dome acts as a buffer zone between the outer climate and the inner microclimate. When the direct solar radiation hits the shade, the heat conducts through the membrane and heats up the air within the cavity. As a result, the warm air rises to the top of the cavity, where we have these openings present, releasing the warm air out. Due to the chimney effect, the cooler air is automatically drawn into the cavity from the ground level, thus creating this continuous flow within the cavity. This principle has been validated by using both computational fluid dynamics simulations and physical prototyping. And it has been observed that this can bring down the temperature inside the dome by 5 to 10 degrees, which is very useful for example, the warm weather climate which we are talking about, but could also be useful where you have cold weather climates. Although the air supported structure and tensile membrane structures are quite common if you see, but the combination into a hybrid structure like in the shaded dome is quite unique and novel, and therefore the design has been granted an European patent. It is something which we are really proud of. Now that everyone is aware bit with the shaded dome concept and how it operates, let's talk about the Freedom Museum. It is located on the edge of the village Groesbeek, as you see here. The old existing museum building was very inward looking and did not just do justice to the location and the beautiful views around. One of the most important starting points for us was to adapt the museum to the landscape. And this theme, you will see, is reflected in our design in various ways, and you will see it coming back as we move along the today's talk. The idea was to reinforce the existing slope and create visual relationship with the valley, and thus connecting the museum with its immediate surroundings. Here, the shape of the landscape was determined by the shape of the new building and the functions which it holds around. When the old museum, which is represented here by these red dotted lines, was demolished, a horizontal landscape plateau was created in front, where events can take place. For instance, there could be some kind of outdoor event. The car parking spaces have been allocated around the periphery, and also the entrance is located in the corner. The museum is aligned towards the landscape, marking clear entrance for the visitors and framing the view over the valley. The dome is also tilted, if you see here, so that it opens towards the front court, which you saw in the previous slides, and hence the plinth is created, which actually acts as the front facade of the building. The museum stands out for its iconic appearance within the green and the flowing landscape design. The building is approximately 64 meters in length and 46 meters in width, and at its highest point, it reaches approximately 12 meters height. The building operates at two different levels, one being the main ground floor level and the other being the basement level. Let's give you a short tour around the museum. So as you visit the museum, you encounter the main entrance. Here you see the plinth kind of peels and bends inwards, thereby creating a niche where the front entry door is allocated. This inviting gesture informs the visitor immediately with the right orientation to enter the building. A simple bronze colored seamed aluminium, or calzip as you call it, was chosen for the cladding of the plinth. The horizontal lines of the cladding in a way also accentuates the sense of movement and dynamism. Once inside, the visitor walks into the front desk where the visitor is welcomed, and the height and the spaciousness of the interior space is quite noticeable as you enter. Due to the large free space that the dome offers, it offers many possibilities for organizing the exhibitions, as there are no restrictive constructive elements like the columns that you might find in any other traditional building. After leaving the court in the clock room, you can choose to visit the temporary facility or the permanent exhibition in your front. Let's begin with the temporary exhibition first. One of the challenges for us was to keep the exhibited pieces in top condition. These pieces are quite old and they're quite fragile in nature. So it was very important that the indoor climate can be managed properly and controlled. Thanks to various methods or measures such as extra insulation of the roof and the box-in-box solution, we were able to achieve the desired level of indoor climate control in terms of temperature, relative humidity. The start of the permanent exhibition begins with a visit to the cinema, where the visitor is introduced to the theme and background of the exhibition. This space is completely closed off from the dome to ensure that the sound and atmosphere is shielded off from the rest of the museum. From here, the visitor enters the permanent space through a wide corridor in the middle of the dome. The dome from within is completely black. It was a deliberate choice to accentuate the focus of the visitors to the exhibition which have been exhibited. The exhibition space is around 1300 meters square area and has an indoor climate in accordance with ASHRAE Class A specifications. The visitors can then move towards the museum cafe. This space has a very different atmosphere and has a more indoor-outdoor feel to it. Here the visitors can disconnect from the exhibition for a while enjoying a nice cup of coffee, and can enjoy the view of the valley from which the Allied divisions once left for Germany. Apart from these exhibition spaces, toilets, shops, the basement accommodates many of museum's supporting functions like the meeting rooms and the working spaces. The museum is also connected to the existing depot below the demolished museum by means of an underground corridor, so that all the supporting spaces remain interconnected. It's also a way of bringing how you can connect the new with the old so that there still remains a connection between them. Just to give you an overview of the internal spaces within Shaded Dome, where you can see the box-in-the-box concept and this immense volume it encloses with it. It's an incredible space to be in, and I would really advise if you have time after the corona to please visit this museum and experience it. It's a very special building.
Which province is it located? Groesbeek?
Groesbeek, it's in the
Gelderland.
Gelderland.
Okay.
Gelderland,
Yeah.
yeah. It's not that close, but
Okay.
you have to make a plan. And of course, for constructing such an unconventional building, you need the right set of tools for the job. We at ZJA worked out the geometric principles for the Shaded Dome and created the computational design tools that makes it relatively easy for us to take the first steps towards architectural design. It allows us architects to pull or push the geometry, but it's also a bit more than that. It's also an informed decision. In order to assess the most aesthetically acceptable and tentative stabilized form, the design requirements are the main input for the parametric model. Although, and therefore we use several generative algorithms, computational algorithms, such as positioning the entrances, optimization in the size of the fabric patches which form the shade and the dome, producing the cable net, therefore also using relaxation and inflation simulations to get the right form. And hence we do have a shaded dome generated in a virtual world, but it's still very much disconnected with what happens in the reality. So this is the first step. We have the shaded dome in the virtual realm. Next step is that our the parametric model which we have generated, it does not provide constructive information yet. The primary function of our software was to determine a rationalized shape and geometry. This geometry is later explored and validated by our engineering partners Royal HaskoningDHV in terms of structural engineering and building physics. They use finite element method analysis and CFD simulations, for instance, to validate. But we indeed, I must admit, we also did our own CFD simulations in-house before we gave it just to see where we stand. So we also had some of an insight into the CFD simulation and how it affects the building geometry, but of course the final validation was done by the engineering partners. After this verification, the latest adjustments were then introduced to our parametric model. Our algorithm then generates relevant files for the components, be it the dome, the cable net, the struts in between, and finally the shade and the suspension cables, which are necessary for manufacturing and assembly of the building. In our construction process, we actually skipped the step where, generally speaking, a fabricator is assigned to create his own set of working drawings, which contributes to extra time, money, redundancy, and inefficiency. Trying to manage the stream of data trees in form of points, lines, meshes was a challenge in itself. Here I would really like to give a shout out to my colleagues at ZJA, Jack Bucker and Ralph Kluth. They played a key role in this regard, and they were able to bring this order in this complex tree of geometry. What we managed to achieve here is a paradigm shift in itself when it comes to design and production workflow. Different parties involved shared their insights with other partners. For instance, Poly-Ned had to share their knowledge about the nuances of fabric materials properties with us. Otherwise, we would have not been able to make such an informed and working simulation. So once we are happy with the design, the next step is the production. Let's follow the same sequence which we already discussed for the shade dome. So first comes the dome. It is made up of 3 layers. There is an interior fabric layer followed by an insulation layer which with R values of 1.6, and finally the exterior fabric. The strategy was to make as many straight strips as possible and few wedges to create a necessary curvature. The sizes of the strips were also determined by the rolls of fabric that were available at the production facility of Poly-Ned. We tried to optimize the shape to get away with doubly curvature occurrences and approximate the 3D model as close as possible. In this entire process, it was important to be very accurate, consistent, and take tolerances into account. Next comes the cable net. It provides the stability to the construction and are anchored to the peripheral concrete walls using the bracket. Each cable we generated needed a number and list of lengths to mark where it intersects another cable. It's a very complex process, and you can get a bit intimidated with the numbers it generates, but because of using this parametric tool, it was really easy to control and get a grip over this entire process. Next comes the struts or the spacers that form the link between the dome and the shade above. The shade consists of steel cables running along the edge, as you can see here. This one, yeah. At the edge of the shade is further tensioned by anchoring it to the ground by using suspension cables. The shade is also connected to the wall via a bracket. This bracket detail is on the middle of your screen. It holds the cable, which you see here, with these harps and the struts with a hinge connection that is further bolted to the concrete wall. For the shade, we had to cut some around 438 patches and weld them together with an overlap of 40 millimeters. Each of these patches had to be labeled in order to know which adjacent patch connects to which. This also provides a sense of organization to the entire scheme. Orientation of the patches on the roll was equally important. This is due to the warp and the weft factors which influences flexibility within the fabric, the material. For our audience who doesn't know what warp or weft are, well, they are the basic components used in weaving to turn a thread or a yarn into fabric. So the forces on each of these patches are actually running in both directions, but they are not really perfectly orthogonal. So we had to rotate each and every patch until the deviation in both directions are the same. As per the shaded dome concept, heat within cavity space between the shade and the dome flow towards multiple openings in the top. If you see, it's mostly here in the top, in order to accentuate the ventilation. Some patches within the shade were introduced with perforations. This amount is determined by a formula. The bigger the dome, the more ventilation patches you need. Here you can see the opaque fabric and the gauze fabric are welded together. I think in this image you can quite clearly see on the top of the shade the openings, where you have this combination of gauze fabric and an opaque fabric coming together. It is also a very important step that in a building, or in case this dome, the rainwater runs along the seams from top from the upper fabric parts to the lower parts. It does sound quite logical and simple, but it's quite a puzzle in itself, especially when you are making each in every patch individually. So to get the right order, it's quite a complex task. Here our computational script helped us in giving this a right order. Once all the components of the dome have been calculated and produced, it is only a matter of assembling and inflating it up on the building site. It took us less than 3 weeks between the moment the parts were delivered to the building site and the moment the construction was actually ready for use. Yeah, it's a nice drone shot. And yeah, this view, for example, you will never experience in today. It's a special view between the shade and the dome. Yeah, I think only in this video you can see that. It was a really special project for us. Everything we had drawn was actually built as it is, without compromises. It was a completely different workflow for us than we are used to. So this has provided us also with a lot of new insights in terms of how you play with a fabric, for instance, and how you play with inflation and how you play with inflatable structures. Roof of the Freedom Museum stood firmly against the heavy snowfall loads, which also took place in the month of February this year, which you all probably are aware of. It also validates the most critical design aspect of the shaded dome, which is to maintain equilibrium between the forces in the dome and the shade. And I think it did quite well in that regard. The partners in this project have managed to achieve good results thanks to the intensive exchange of knowledge and collaboration. For us, we had to share our know-how in terms of geometry with different partners and vice versa. Though it may sound really logical, but it is not so obvious in our day-to-day construction practice that to share knowledge without hesitation with any other next party. But by doing that, you also are able to push the boundaries in a better way, and you can achieve magnificent results eventually. By this, I hope you all enjoyed and took something away from this presentation. It's a very complex process. I tried to boil it down a bit. I hope you take something away from it, and I would like to really say thanks for taking time out. And yeah, I'm now open for any questions if you have.
Thanks a lot, Anurag, for the interesting presentation about the shaded dome.
Thank you.
It's really nice to see this whole project coming together from this parametric model, where all these detailed requirements are in, even the allocation of all the patches, in order to have the rain dripping off in the correct way. What I was curious about, this is actually a multi-company project.
Yeah.
How did that start? Because I can imagine it can be experienced as a really scary thing to share your knowledge with other companies. So how did that?
It's I think it is indeed an incredible process. Like every company is different and they have their own interests and shares. But in this project, they decided to come together and to join hands for the betterment of and developing a technology which didn't exist. So that's why if you go, there's like a boundary. You have to break through those boundaries to achieve these kind of outcomes. Otherwise, you can't get a patent for something like this. It is because I can imagine there's an engineering company, so they have certain level of expertise.
Yeah.
For example, we bring a certain level of expertise in terms of architecture and how you can connect this with the functional requirements. And for example, in this case, the fabric and the inflatable structure, that's also a very specialized domain.
Yeah.
So it's incredible that these three expertises kind of came together in one, and they're ready to share this knowledge in one common bowl, which kind of came up. So
yeah, that's quite. Yeah,
so really, that's what I think. Also, this was also my also one of the drivers for today's talk, that you need to have collaborations to get products which are outstanding, and it kind of prove, it's like a proof of concept that if you do this kind of collaborations for more in more different areas, you can get sometimes unexpected results which you are not even expecting.
Yeah, because I expect that these kind of examples will become more and more often visible in our day-to-day industry, where we collaborate in a digital way comparable to the shaded dome. So that's really nice. So this is the first big structure that is constructed with the shaded dome.
There had been quite a few prototypes which are already being built. but this is one of the first actual building project which has been built, and but we do expect maybe in future there'll be more similar buildings popping like. In this case, it really made sense because the old structure also had this roof structure, a fabric roof structure, and Shaded Dome has a bit of a similarity in terms of architectural vocabulary, and it also needed clients who are daring to take the extra plunge to try something new.
Yeah.
And hats off to that more and more people and clients are willing to take chances on new technologies.
Yeah.
But of course, there had been proof of concept before, so they were convinced that it works.
Yeah.
But it was great that we were able to develop it into a full-fledged building.
Yeah, and it's also quite funny that that the application has become or is a museum, because in the beginning of your presentation you were talking about tennis fields and things like that. So.
Yeah, exactly. So so these kind of projects are very they're not linear. So you started developing something for a client who is, for instance, it started with Qatar, and at that time the client was the Qatar government who wants to have these training facilities in the warm weather climate conditions, and there you need this dome.
Yeah.
But then it could also be translated into various different functions, and there's this sense of scalability.
Yeah.
So you can have really small code, but you can also expand it. And I think the biggest advantage is it creates a space which is large span, which doesn't have any columns or any constructive restrictions, and that makes it very flexible of housing different functions within.
Yeah. So for the Qatar World Championship, you still have some time to because that's in 2022, right?
Yeah.
So you still have some time to develop some shaded domes over there. Is there actually a constraint on the size of that you can actually make it?
No, I think there are some constraints. Of course, you can grow, but the only thing is the bigger the radius of your dome becomes, the more overpressurized you have to do the dome.
Okay.
And that means right now, for example, if a generic situation, if you see, it's I think 3.5 or 2.5 millibar pressure which you create within the dome.
Yeah.
But as the dome becomes big and you want to have higher clearance on the top or make it more rounded, so more air you have to push. So that there are also limitations. You can go to a certain extent. Otherwise, otherwise it will become more flat in nature. The dome will be very higher, but it will be much more shallow.
Yeah. So basically, the energy usage is a constraint in that sense.
It's more also in terms of the geometry. So if you make a really big dome, it might look very. You can of course go to any extent. You have this SML XL format. You can keep growing. It's inflatable. It's a balloon. You see eventually, but then there'll be more technical challenges coming as well, in terms of, for example, safety, because you have a dome and you have entry-exit points. So you have to also control those entry-exit points, right? You have people who are entering, and then you have to allocate number of doors for that kind of occupancy.
Oh yeah.
So I think it's possible. The scalability is possible, but so this is the first step, and I think it could be scaled up. But then I think more investigation needs to go into that.
Yeah, you need to do that. You need to do intermediate projects in order to.
So it's a baby step. So you start with a small. We reach this medium level, and probably it's going to be large for next time.
Definitely. Also nice that this dome was tested during the snowfall. But in this picture, I didn't see any snow on top of the dome. Is that does that melt really rapid, or how does that?
No, during this snow, it was quite heavy.
Yeah.
There was indeed. That's the thing about this structure. You have an inner dome, and you have this shade on top, which are kind of interrelated with the spacing, and it kind of compensates itself. So, for example, if there's a lot of pressure on top, the dome tries to. You can over pressurize the dome so that it kind of retains the shape. In this case, the snow had to be cleared out.
Yeah.
Because there's this surface is not an anticlastic shape, but it's more like a synclastic. So the snow is kind of contained. So they had to clear the snow out, but as soon as the snow was cleared out from the top of the shade, it retained its shape, because then it reached its equilibrium position back.
Yeah, but do they have to shovel on the top of the?
The fire brigade has to be employed, who had to take the snow out.
Okay.
On top.
Yeah. Okay. Interesting. That's quite cool. And I also have this really production-wise question. This is just a huge sheet of fabric. So how is this transported? Is it just one giant roll of fabric, or is it?
No, there are two ways. So there are some fabrics which are assembled in the. We have Poly-Ned has a facility. So it's like a big ground.
Okay.
So some of those fabrics were glued because it's a process where it's a heat. They're kind of glued, but it's in a molecular level. They're glued, and many of these fabrics you can see they came in these rolls. So you can cut out these separate patches out.
Yeah.
Then you weld them together.
Yeah.
And then you get this, indeed, as you said, segments or these big patches of fabric which are. And then those were transported to the site, and they were again connected or glued on the site again.
So it were just bigger parts.
Yeah, bigger pieces which are, and you will see that there are these 3 separate patches which goes around, and they form the one big patch or big shape.
Yeah.
But it goes quite fast. It's really like a jigsaw puzzle. So you have all the pieces of the puzzle. They're all there. It's just a matter of closing it off and inflating it, and then you get it.
Yeah, and you have to completely trust the notations or the
exactly.
The
so
numbers.
That's why I mentioned you have to be very precise and accurate with how the connection numbers and these things work, because you can't make a mistake there. Otherwise it can really make your you have to start again. There's no going back in that. So that's what this is also a process. When we made prototypes, we kind of understood how this thing works. So we made mistakes in the beginning, but we improved upon it as we moved further along. And now we have reached a level that the software generates the patches, and there's a clear manual of how you should align it. And anyone you can give to them can glue it and can get it fixed as per our design requirements.
Yeah, cool. There's actually a really other way of constructing that I am used to, at least, because it's normally steel or concrete. Really, it's just a stable form and not like an inflatable structure. Yeah, so
that's why also if you talk about the structural aspect, it's also quite challenging, because if you talk about a conventional steel structure, more or less how the material will behave.
Yeah.
But in this, it has a lot of dynamic forces. It can change based on how the inflation is happening and how the air pressure is changing. So to simulate that, also you need. That's why you have to use this finite element method, and it's a very different approach because they have dynamic loads, which keep on changing. So it's not that easy to simulate in conventionally speaking.
Yeah, I can imagine that. But does that also mean that during, for example, storms, you have to increase the pressure within the dome or decrease it?
You need to. I think if you have really bad weather outside, if it's stormy weather outside, generally, for example, if the inside pressure is, let's say, 2.5 millibar, maybe it has to reach to 6 or 7 or 5. So you compensate the pressure difference.
So you make it really.
So exactly. There's also a supporting system which is working, which is pushing in the air and pushing air out. And that has it's also a specialized thing how it maintains based on the weather conditions.
So that's also
it's a dynamic system. It's an automated dynamic system which is working in the background, which is hidden from public eye. People don't see it. It's there behind.
That's actually you don't create a building. You create a living creature, a giant lung.
Yeah, it's a living. Indeed. It's alive.
Nice. That's great. So are there actually projects in progress which you can talk about that are coming, or
I'm probably not allowed to talk about, but if it comes, you will please look at our website. It will be published there. We also have Shaded Dome. It has its own individual website as well, which is this conglomeration of these 3 companies coming together.
Yeah.
So probably you will also find there for the latest news.
Great. I'm excited. Looking forward to seeing all kind of just shaded domes popping up in the Netherlands.
Yeah, it's in Netherlands or even abroad.
Yeah, or Qatar.
Yeah.
Let's hope for that. Yeah. Well, I think we'll wrap it up at that moment. Thank you all for watching. thanks a lot for the presentation, Anurag. It was really amazing that you came here and gave this presentation about the shaded domes.
I hope you all learned something different, or it kind of maybe triggered a new way of thinking towards design, which is not really conventional.
Yeah, for me it definitely did, because designing with fabric is especially something, for me it's quite new, and it's quite, it's something to be open to and to be inspired by. So because in some projects it might be interested to use these kinds of technologies.
Yeah.
So in 1 to 1.5 weeks we will be back together with Royal HaskoningDHV. Keep the website, keep a close eye on the website for the exact time and the title of the presentation, and I hope to see you back then. Thank you all for watching, and see you next time. Bye.
Bye.